Everyone. So this is the second session of the advances in food analysis, and the topic shall be covering today is the scanning electron microscope, that is SEM. So what are the major imaging functions in a microscope? So what basically does a microscope do? It magnifies, resolves features, generates contrast, and captures and displays images. So here's the difference between transmission electron microscope and scanning electron microscope. About transmission electron microscope we'll be studying in the further slides, but just a brief difference between the two is that the source is the electron source is the same. Then transmission electron microscope has a condenser just below the source, and then there's an object, and then the objective or the aperture. And in transmission electron microscope it can be seen on the fluorescent screen, and in SEM we have the computer and which is attached to detector, and we can see through the monitor. So this is how an ultra high resolution scanning electron microscope looks like. The How's the breakdown of an electron microscope occurs? So in simplest terms, a SEM is really nothing more than a television. We use a filament to get an electrons, magnets to move them around, and a detector acts like a camera to produce an image. That's how simple it is. So scanning electron microscope is used for inspecting topographies of specimen at a very magnifications using a piece of equipment called a scanning electron microscope. SEM magnifications can go to more than 3 lakh times, but most of the semiconductor manufacturing applications require magnifications of less than 3000 times only. SEM inspection is often used to analysis of die package cracks and fracture surfaces, bond failures, and physical defects on the die or package surface. During SEM inspection, a beam of electrons is focused on a spot volume of the specimen, resulting in the transfer of energy to the spot. These bombarding electrons, also referred to as primary electrons, dislodge electrons from the specimen itself. The dislodged electrons, also known as secondary electrons, are attracted and collected by a positively biased grid or detector and then translated into a signal. To produce the SEM image, the electron beam is swept across the area being inspected, producing many such signals. These signals are then amplified, analyzed, and translated into images of the topography being inspected. Finally, the image is shown on a CRT. The energy of the primary electrons determine the quantity of secondary electrons collected during inspection. The emission of secondary electrons from the specimen increases as the energy of the primary electron beam increases until a certain limit is reached. Beyond this limit, the collected secondary electrons diminish as the energy of the primary beam is increased, because the primary beam is already activating electrons deep below the surface of the specimen. Electrons coming from such surfaces depths usually recombine before reaching the surface for emission. Aside from secondary electrons, the primary electron beams result in the emission of backscattered electrons from the specimen. Backscattered electrons possess more energy than secondary electrons and have a definite direction. As such, they cannot be collected by secondary electron detector unless the detector is directed in their path of travel. All emissions above 50 electron volts are considered to be backscattered electrons. Scanning electron microscopy. The backscattered electron imaging is useful in distinguishing one material from another, since the yield of the collected backscattered electrons increases monotonically with the specimen's atomic number. The backscatter imaging can distinguish elements with atomic number differences of at least 3, that is, materials with atomic number difference of at least 3 would appear with good contrast on the image. For example, inspecting the remaining gold on an aluminium bond pad after its aluminium ball bond has lifted off would be easier using backscatter imaging, since the gold isolates would stand out from the aluminium background. A SEM may be equipped with an EDX analysis system to enable it to perform compositional analysis on specimens. EDX analysis is useful in identifying materials and contaminants as well as estimating the relative concentrations on the surface of the specimen. Comparison of optical microscope TEM and SEM. The principal features of an optical microscope, a TEM and a SEM, is drawn to emphasize the similarities of the overall design. So, in a light microscope, the image is viewed directly and the light source is present, followed by a condenser and then an eyepiece. A transmission electron microscope has magnetic lenses and then a specimen is placed. In a cathode, in a scanning electron microscope, there's a lens, then there is a detector, and then it is connected to a CRT. Electron microscopes. The electron microscopes are scientific instruments that use a beam of energetic electrons to examine objects on a very fine scale. Electron microscopes were developed due to the limitations of light microscopes, which are limited by the physics of light. In the early 1930s, this theoretical limit has been reached, and there was a scientific desire to see the fine details of the interior structure of organic cells. This required 10x plus magnification, which was not possible using current optical microscopes. So this is a scale and microscopy techniques, that is the microstructure ranging from crystal structure to engine components. So here the structure determination and the fracture mechanics, that is a cracks inside a structure, can be determined. So inside optical microscope, we can see from a range of 10 meter to 10 to the power minus 4 millimeter, and a SEM can see between 10 to the power minus 4 to 10 to the power minus 9, and an XRD can see, X-ray diffraction system can see 10 to the power minus 10. So that is how it can be deep. That's all for this session. Thank you.